Today we want to talk about a very important concept in electrostatics. That concept that we're going to see today is electric multipoles. Okay, so the question that we need to do first is what happens when we have a lot of electric charges on a certain distribution that, well, I have drawn here. See that we have a charge Q1, Q2, all the way up to Qn. And well, we have a reference system here. Okay, in this reference system, well, we can locate a general charge named as Qi. Okay, so this whole set of electric charges is going to generate some electric potential in the space. Okay, in this case, we put a general point of the space x, y, z, and we name it as P. Okay, so we want to measure what is the electric potential at P. Okay, due to all these electric charges that we have here, which is a finite set of charges from 1 to n. Okay, so we know that the general formula for the electric potential is this. If we want to measure the electric potential on a vector r, well, this is going to be just the sum from I equals 1 to n of 1 over 4 pi epsilon 0 times Qi over Ri, where Ri is just the vector that points from the charge Qi to the point P. Okay? So we need to calculate this for every charge that we have on the distribution and then sum that terms to get what is the total electric potential on the point P. Okay, so that is what we are going to do today in a very precise way. So first of all, we need to calculate what is the vector r, okay, in terms of this little r and ri. Well, we know that, well, these are just vectors, so we can sum. We are going to get that ri plus r is equal to little r. And from here we get that r is equal to r minus ri. Okay, so here ri is going to be, well, just the magnitude of the vector. And in this case, well, this will be ri. So we know that to find the magnitude, we can just take the dot product with itself, with the dot product between Ri and Ri. This will give us the magnitude squared of the vector. Okay, so this is just going to be R minus Ri dot R minus Ri. And this is going to be, well, it will be R squared plus Ri squared and then minus 2 times R dot Ri. But we know that, well, this is equal to R times Ri times cosine of theta I, where theta I is the angle between Ri and R. Okay, so we finally get that Ri is going to be, well, the square root of r squared plus ri squared minus 2 times ri cosine of theta I. Okay, perfect. So in this case, what we are going to do is to take r squared as a factor, a common factor. So that is going to give us r squared times 1 plus ri squared over r squared minus 2 times ri over r cosine of theta I. And well, looking that r is positive because it's a magnitude, well, we can just cancel the square root with this square to get the next r times the square root of 1 plus ri squared over r squared minus 2 times ri over r cosine of theta I. Okay, so we get then that the electric potential at vector r is going to be the sum from I equals 1 to n of qi over 4 pi epsilon 0 times 1 over ri, and that is 1 over r times the square root of 1 plus ri squared r squared minus 2 ri over r cosine of theta I. Okay, perfect. So in this case, well, we have an expression that turns to be more difficult than what we had, but we need to do a little bit more of work to see what will happen. Okay, now after that we found this expression, well, what we are going to do is to name t as ri squared over r squared minus 2 ri over r cosine of theta I. Okay, this change of variable is going to be very useful because if we see we then need to calculate this thing over here, okay, a function of t. And well, what we can do is to use the Taylor series expansion for this function that is very known. It's not very hard to show that this function in an expansion is going to be equal to 1 minus 1 half t plus 3 over 8 t squared minus 5 over 16 t cubed, and then plus, then so on and so forth. Okay, so we are going to use this formula with this definition of t. And before doing that, what we are going to do is to make an assumption. We are going to assume that r is much bigger than ri. Okay, if r is much bigger than ri, then the quotient ri over r, well, it will be almost 0. Okay, and that means that, well, we are measuring the electric potential on a point P that is very far away from the distribution of electric charges that we have. Okay, making that the magnitude of this vector r is much bigger than the magnitude of this vector ri that points to the charge qi. So if we do this, then we are going to get that, for example, ri over r to the third power is going to be, again, almost 0, and we are going to well, cancel all the terms that are raised to the third power and to the fourth power and to the fifth. So we are just going to get to the quadratic term. Okay, so that means that, well, this term, looking that it depends on the quotient between ri and r and is raised to the third power, this will be almost 0. So we are not going to count this term. Okay, so we are going to get that 1 over the square root of 1 plus ri squared over r squared minus 2 ri over r cosine of theta I is going to be equal to 1 minus 1 half t, but t is all this, okay, and then plus 3 over 8 times this thing raised to the third power, sorry, to the second power. Okay, so we are going to make the development of this, and this is 1 minus 1 half ri squared over r squared plus ri over r cosine of theta I, and this will be plus 3 over 8 times ri to the fourth over r to the fourth minus 4 times Ri cubed over R cubed cosine of theta I plus 4 Ri squared over R squared cosine squared of theta I. As we mentioned, these things are going to be almost zero, so we are going to ignore them to get 1 minus 1/2 Ri squared over R squared plus Ri over R cosine of theta I, and then plus 3 over 2 Ri squared over R squared cosine squared of theta I. So taking the common factor Ri squared over R squared, we are going to get that this is 1 minus Ri over R cosine of theta I plus 1/2 Ri squared over R squared times, well, 3 cosine squared of theta I minus 1. And again, let me remind you that this is 1 over Ri, okay? The term that goes here. So to calculate the potential, well, we just need to multiply that thing that we just found to this expression that we have here, okay? So let me copy. And this will multiply all this expression here. Okay. If we multiply this factor 1 over R to all this expression, we are going to get that the potential on R is going to be the sum from I equals 1 to N of Qi over 4 pi epsilon 0 times 1 over R plus Ri over R squared cosine of theta I plus 1/2 Ri squared over R cubed times 3 cosine squared of theta I minus 1. Okay, and then what we are going to do is just to split the sum in these three terms, okay, to get that the potential is going to be the sum from I equals 1 up to N of Qi 4 pi epsilon 0 times R, then plus the sum from I equals 1 up to N of Qi Ri cosine of theta I over 4 pi epsilon 0 R squared. And then just to finish, this would be plus 1/2 the sum from I equals 1 up to N of Qi Ri squared times 3 cosine squared of theta I minus 1 all over 4 pi epsilon 0 R to the third power. Okay, just as a definition, this is going to be the monopolar term of the potential, of the electric potential, okay? This will be the dipolar term, and this will be the quadrupolar term. Okay, so what we just found here is an approximation of the electric potential measured at a point P due to a distribution of n electric charges on the space. Okay, if we make an approximation up to the second power of the Taylor series expansion, we get three terms, okay, that are going to be very important: the monopolar, the dipolar, and the quadrupolar term. Okay, and yeah, well, this will be the final result of the video.